Hello, everybody. Welcome back. Today we're going to go over section 3.5, which we talk about the critical points and the first derivative test. In section 3.4, you learned how to find where a function was increasing or decreasing, and you learned how to find x values where the tangent line is horizontal. Today, we're going to take that information that we already know how to find and use that to determine some aspects about an original function. We will use where my function is increasing or decreasing to find any turning points, or what we will call local maximums or local minimums of your function. So how can we use the derivative to describe aspects and characteristics of the original function? That's what we're going to learn today. So the objectives today are to determine what's called critical values or critical numbers of a function. And then once we have those critical numbers, we will use what's called the first derivative test to find any local extrema. So to give you an idea of what we're doing, it's best to kind of show this with a picture. So I have a picture that I artistically drew here. And suppose we have some function curve like so. On this particular function curve, I have two turning points. This is a turning point, and this is a turning point, meaning that my function is going in one direction and then turns around and goes back the other way. In this side, we would have learned from section 3.4 that on this part of my graph, my function is decreasing. So I'll write that as DEC for short. My function is decreasing, it's going down. Now remember, when you have to find where your function is increasing or decreasing, you have to trace it from the left side to the right side. So if you start on the left side of your graph and draw it with your pen, on this side, we're going down. So my function is decreasing. On this side, you're going up and drawing it. As soon as you have to go up, you would say that your function is increasing there. And then I am going up, 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 and then I have this other turning point right here when my graph turns around and starts going back down again. So we have this decreasing again on this side. Decreasing, increasing, decreasing. And as of last section, this is where we would have tied this to the derivative. If your function, your original function, is decreasing, that means that the derivative function there is negative. Any value of your derivative would be a negative number on this segment. If your original function f is increasing, then you can tie that with the derivative by knowing that the derivative f prime is positive. And then again, we have my function decreasing, which means your derivative f prime is negative. So as of section 3.4, you could have found this. My derivative is negative, means my function is decreasing, and vice versa. My function decreasing means my derivative is negative. My function increasing means my derivative positive, and my derivative positive means my function is increasing. They go hand in hand. We learned how to create intervals where my function is going down, up, and down, etc. That would have been last section. This section, we can kind of tie that together with locating these turning points of my graph. So if I look at this turning point, where my function is going from decreasing to increasing, this turning point here, we would call that a local minimum. Local minimum, because it's kind of the bottom of a ditch right here. It goes down and then starts going back up. That is the general characteristic of any local minimum. A dip in your graph is going to be characterized by a decreasing to increasing switch across on either side of this turning point. Similarly, if I come over here to this turning point, this is kind of like the top of a hill. We would call this a local maximum, because locally in this small little region right here, I have a topping out point, a maximum point where my graph turns around, before my graph turns around and goes back down. A local maximum, therefore, always has to be characterized by it increasing on one side and then turning around and decreasing on the other. Otherwise, you wouldn't have a local maximum. It's got to go up on one side and down on the other. Therefore, if we can describe this, if we can say a local maximum has to have my function increasing on one side and decreasing on the other, I can tie that to the derivative. My derivative therefore has to be positive on one side and negative on the other, because those two things go hand in hand. What we do in practice is, instead of here's the original function, can we look at the turning points? It's, can you figure out where the turning points are if all we're looking at is the derivative itself, not the original function? So let's pretend that I don't have the original function and I don't see the graph of it. Maybe you can find local maxes and mins by figuring out that your derivative is negative on one side and positive on the other. Decreasing to increasing on your function means your derivative's negative and then has to go to positive. A local maximum means that your derivative is positive and then it has to switch to being a negative, since these two things go hand in hand. That's the idea of this section. Can we locate local maxes and mins by using the derivative and what it equals? Let's consider this turning point again, the local maximum. This local maximum is at the point 2, 2, and it corresponds to an x value of 2. So we have an x value here of 2 and a y value of positive 2. This x value, where the local maximum occurs at, that is called a critical number. A critical number is any x value where there is potentially a local max or a local min. For my local minimum over here, the x value that corresponds to this point is -4, and the y value is -3. But this x value, this x value -4, this is also a critical number. So in a universe where I don't see the original function, I'm not sure what exactly it looks like, I can use the derivative to figure out where the derivative is negative and positive and negative. It helps me describe what my original function is doing. Also, if you can find these particular x values where critical numbers are, you have a really good idea of where there's a local max or local min. And the nice thing about critical numbers is that when you look at the top or bottom of your hill, if you think of the derivative as being these tangent lines, on this side of my local minimum, my tangent lines are all negative, hence why the derivative is negative. Or the tangent lines all have negative slope, that is. But once you get to the bottom of this trough here, just for a split second, my tangent line is flat. And when your tangent line is flat, that means your derivative is 0 there. Similarly, if I'm going back up this hill, pretend I'm drawing all my little tangent lines, all of these little tangent lines have positive slope. That's why the derivative is positive. But once you get here at the top of this hill, there for a split second before it starts going back down, the tangent line is horizontal, which means the derivative is 0. We can use the derivative to find critical numbers, because at critical numbers, if there's a local max or a min, the tangent line has to be 0. So this is a picture of all the terms and what we're going to be doing. Let's kind of show you how this all works in practice. We'll go back to our definition. All right, so here's where they formally define everything. The points where a function changes from increasing to decreasing or vice versa are called local extrema. And we had pictures of those on my little doodle there. We had a local min and a local max. So local maximums are the tops of these. It's localized high points. And local minimums are the localized low points on your graph, low turning points. We say that these local maxes and mins occur at the x value. They're very particular about using the word at. So we say that the local max is at x equal whatever, and the local maximum is equal to whatever the y value there is. And that's kind of a terminology thing. So you'll hear me say this a lot today. I'll say the local min is at x equal blah and is y equal, etc. So we always say at the x value and is the y value. This is where it starts getting interesting. If a function is continuous on an interval, that just means that it plays nice, and there is some number c inside that interval. If the y value at c is either a local max or local min, meaning you're trying to find your local max, if it is a local max or min, then it must be that the derivative is 0 or that the derivative does not exist. This is a powerful statement. This is saying if you're going to find where your maxes and mins are, the ticket is that those will only happen when the derivative is 0 or where the derivative does not exist. So this would be domain restrictions of the derivative. Now, we have to be careful here. When I talk about domain restrictions of the derivative, they would have to be new domain restrictions of the derivative that the original function does not have. I will have to, I'll elaborate more on that a little bit later. This is a very handy statement. If I'm telling you we're going to find local maxes and mins using the derivative instead of looking at a picture, then this is the ticket. Those local maxes and mins will occur wherever you find that the x value is 0 and wherever you find your derivative does not exist. It's a good thing to know. Now let's expand on that derivative does not exist thing. Values c, those specific numbers where local maxes and mins may occur, this is where we formally name them. They're called critical numbers. You can also see it written as critical values. But those critical values where there is a potential max or min occur, as we said, where the derivative 0 or the derivative does not exist. But if I want to elaborate on this a little bit, the values where your derivative may not exist, for those to be potential maxes and mins, they have to be new domain restrictions that the derivative has that the original function does not. So let's say your original function has no domain restrictions. Any value of x can be plugged in at any time, no problems. If you take the derivative and you find that the derivative does have a bad value of x, it does have a domain restriction, then that's a new domain restriction that came out in the derivative function. That the original function was fine. It did not have that domain restriction. But now I do have one that came from the derivative. So when that happens, that's a new domain restriction, and those are also potential maxes and mins. So the connection you need to make is that critical numbers are potential maxes and mins, maximums or minimums. Let's try that again. Minimums. There we go. Critical numbers are x values. They're x values that are maybe where a max and min occur. We don't know. But if we're going to find what those potential max and min points are, you either have to find where the derivative is 0 or new domain restrictions of your derivative. And don't worry, I'm kind of over explaining everything. We'll practice this. You'll see what I mean. The only, kink in this is that if you get a critical number, I say they're potential maxes and mins because there's not a guarantee that they're actually going to give you a local max or min. You could get a critical number. You can think of a critical number as being a point of interest. A critical number, you might find, x equal 2 is a critical number. But that doesn't necessarily mean it has to correspond to a local max or min. X equal 2 would be a point of interest in that example, but you'd have to test it. You would have to check to see if there was a max or a min there. So that is what the first derivative test is for. Now there's a lot of words here in the steps, but it amounts to, first, find these critical numbers. Find these interesting values of x where a max or min may be. To find whether or not they actually do correspond to a max or min, you create a draw an analysis line, or that is to say, a number line, and put your critical numbers on the number line. You will then use the derivative function and find where the derivative is positive and negative on the number line. That lets you know where your function is increasing and decreasing. You would have done this somewhat in the last section, section 3.4. If you know where your function is increasing and decreasing, if you know those intervals, you can put 2 and 2 together and find where there's a local max or min. So let's get some practice doing this, where we find these interesting x values called critical numbers, and we test them to see if they actually give me a local max or min on my graph. Here's what something might look like. Problem number 1 says, consider the function f of x is minus 2x squared minus 3x minus 5. And this one, they broke up into 2 parts. Part A says, find the critical values for the function. Now, critical values are these interesting values of x, where maybe there's a local max or min. To find critical values come from 2 places. 1, they happen when the derivative is equal to 0. So if I'm going to find these interesting x values, I have to find, firstly, where the derivative f prime is equal to 0. So this one's not too bad. If I'm going to find where the derivative is equal to 0, that means you have to take the derivative and set it equal to 0 and solve for x. Let's make a note of that. How you do this part is you take the derivative, set it equal to 0, and solve for x. Now, you would have done this before in section 3.4, but the way they phrased it then was they said, find the points where your tangent line is horizontal. It's the same exact thing, except now I'm calling it critical values. It is the same thing. Take the derivative, set it equal to 0. That's where your tangent line is horizontal. So here's my original function. Let's take the derivative of it. Derivative of minus 2x squared, we do a power rule on that. We get minus 4x. The derivative of 36x is 36, and the derivative of negative 5 is 0. So here's my derivative, and you're supposed to take that thing, and you set it equal to 0. Why is it, and this is an aside, by the way, why are we interested in particularly 0? Because this is the derivative means slope of a tangent line. 0 is the value where your tangent line is horizontal. And your tangent line is horizontal at these tops and bottoms of these hills. So it's no coincidence that we are setting this equal to 0. 0 is this horizontal slope. So just FYI, that's why it's 0 particularly. Take your derivative, set it equal to 0, solve for x. You have minus 4x equals 36. Divide both sides by minus 4. Get 36 divided by negative 4. Which is negative 9. This is a critical value, or you can say it's a critical number. So this means that this is a potential max or min on this graph. We don't know. We'd have to test it, but it's potentially one. The second place that these critical numbers may come from is 1, where the derivative is 0, and 2, any new domain restrictions of f prime of the derivative. So when I look at my derivative function, here it is. I'm looking for quote, quote, bad x values. Are there any x values that might make a denominator 0 here or something like that? This function doesn't have a denominator, so there's not any domain restrictions that I see. There's no square roots in I have to worry about being negative. There's no fractions I have to worry about the bottom being 0. So that is to say, my derivative function has no domain restrictions at all. So of course there aren't any new domain restrictions. So we're just going to a note here that we don't get any other critical numbers besides the one that we already got by setting the derivative equal to 0. So we take this thing, we have one critical number, one x value of interest, only one. And then we move to part B. This is where we actually do what's called the first derivative test. Now here it goes. The first derivative test says that you take your critical numbers and put the critical numbers on a number line. Create a line where all the way to the right is infinity and all the way to the left is minus infinity. And this is supposed to represent the whole entire domain of your original function. But on this number line, you're not going to put any other numbers except for your critical number. So maybe in the middle here, you put your critical number -9. Now this you can kind of denote by a open circle. This is a break. So at x equal 9, we know my derivative is 0, right? We set the derivative equal to 0 to get -9. So we know that the tangent line is horizontal at x equal -9. It's horizontal there. Well, I'm just going to make a note, not that this is required, but just a note, the derivative is 0 at this guy. Keep that in mind. So here's how you figure out whether -9 corresponds to a local max, a local min, or neither. You pick a point on the left and right of -9 on this interval and this interval, and you test this interval. You do this just like you did last section in section 3.4. So pick a test point on the left and right of -9 and see what your derivative is there. So let's pick a point in this interval between -infinity and -9. Let's say I choose a test point of -10 on that side. Over here, pick a number between -9 and infinity. It can be any number you want, any number in between there. So why don't I choose 0? Those are test points, and you're going to plug your test points into the derivative because you want to see what value you get. So for this interval, right here, -infinity to -9, I take a test point -10, and I'm going to plug this into the derivative function, not the original, the derivative. So here's my derivative function all the way up there. I'm going to plug -10 into that. I get -4x -36 if I plug -10 into this thing. Here it is. This becomes 40 minus 36, which is 4. I don't so much care what the number itself is, but I do care that this is a positive result. If I get a positive result out from the derivative, that says something about the original function. We know that if the derivative is positive, that does correspond to my original function increasing. So that means on the interval I pulled that test point from, -10, that interval on that whole entire region, my function is increasing. So let's write it out. F, the original function, is increasing on that first interval, left, right, -infinity to -9. If I scooch on down here, I just tested this interval here, so I'll write here that my function is increasing on that interval. Let's do our second test point. I have this interval right here, -9 to infinity. I'm going to pick a number in between there, 0. Let's plug that into the derivative and see what we get. Make sure that you plug it into the derivative, not the original function. So I have -4, 0 minus 36. My derivative function's up here, and I'm plugging 0 into that. So you get -36. this tells me a lot of things. I have a negative number out from the derivative function. So what does that tell me about the original? That tells me that my original function, f, is decreasing. Those two things go hand in hand. So I can write that the original function f is decreasing on the right of -9. It's increasing on -9 to infinity. So I'm going to write here DEC for short. We said, let's back up here. We had said that -9 was a critical number. We said that that was an interesting point. -9 is possibly a max or a min or neither. Let's look at the data of what's going on either side of -9. To the left of -9, my function is increasing. That means it's going up. To the right of -9, my function is decreasing, going down. So if I put 2 and 2 together, if my original function is going up and then going down, what does that mean has to happen at the x value -9? That means I have to have a turning point of a local maximum. My function's going up and it's going down after that x value. So that means there has to be a turning point. Goes up and then goes down, up and then down. There has to be a max. So somewhere above x equal -9, it's going to be a maximum. So we would say, this is where I'm going to be particular about the language, there must be a local maximum at the x value, x equal -9, that critical number. There must be a local maximum at x equal -9. And we got that by using the first derivative test. First derivative test just means that number line thing we just did. Finding where my derivatives, negative and positive. All right, we're almost there. We know where the local maximum is occurring at. It's occurring at this x value. But that's only one half of the picture. If I have an x value of -9, it would be really great if I knew what the y value was. So let's plug this x value into the original function to get the y value. Remember, the original function is what cranks out y values. So you should plug x equal -9 into the original function to get the y value. So when you do that, you go way up here, way up here. You plug -9 into that, the original function, f of -9. It's -2 times 9 squared minus 36 times 9 minus 5. I had previously punched this out, but this gives you 157. So my y value at -9 is 157. This point is way up high. But here's my point. My point, xy, occurs at -9, comma, 157. X value of the maximum, that's the y value of the maximum. So we would say that the local maximum occurs at x equal -9, and the local maximum is 157. So the local maximum is the height. We say the y value is actually what the max is. It's the height, 157. It occurs at -9, and this is the xy coordinate point that you can plot on a graph. This is my local max. So I did a lot of explaining there, taking lots of time to do so. But once you get in the habit of doing this, it actually goes by pretty quick. You end up not having to write out so much. So let's move to another problem and another one and get some more practice doing these. Now, number 2 is slightly different. We're going to be doing the same stuff, but they present the data differently. It says, suppose that the derivative of the function f is already found and factored to be this. So if we pause here without reading the rest of it, what they did was they didn't give me what the original function was. They didn't tell me what f was. We don't know what f is equal to, but they did give me the derivative function. In other words, they found the derivative for you and they factored it for you and said, bleh, there it is. So we don't know what the original function is. We can't graph it, we can't see it, we don't know anything about it. But what we do know is this is its derivative, and it's already factored for us. So then, we look at part A. Part A says, find the critical values for the function. Find the critical values for the function. Now, this is where we have to remember that critical values or critical numbers come from 2 places. 1, setting the derivative equal to 0, and 2, any new domain restrictions of the derivative. So let's start off with 1. Set the derivative f prime equal to 0. That's how you get sum of the critical numbers. They occur when the derivative is 0. Well, there's the derivative. It's already been found for me. Let's set that equal to 0 and have at it. So we are setting this equal to 0. We're forcing it to be 0. Now, when you have that happen, and this is already factored, this is 3x times 5 minus x squared times minus x minus 2. The only thing that makes something multiplied like this equal to 0 is if the separate parts are set equal to 0. So what we do is we kind of split this. This is the same as saying 3x equal to 0. This is the same as saying 5 minus x squared is equal to 0. And this is the same as saying minus x minus 2 is equal to 0. All of those factors split up, which then you can solve for x. If I divide by 3 here, we get x equals 0. That's one critical number. From this one, if you square root both sides to get the 5 minus x, square root of 0 is still 0 over there. If you add the x to the other side, you get x equal 5 is another critical number. So I've got 1, 2 critical numbers, and then as soon as you solve this fella equal to 0, you'll have 3. Add the 2, you get negative x is equal to 2, or that is to say, if you multiply by a negative, x is negative 2. I have 3 critical numbers. That means I have 3 potential locations for being a maximum or a minimum. We would have to test those to see if those do correspond to maxes and mins, or if they correspond to nothing. The second area that we have to consider for critical numbers, like I said before, it's 1, where is the derivative 0? And 2, where are the new domain restrictions of the derivative? So let me write that down. New domain restrictions of the derivative. When I look at the wording here, it says, suppose that the derivative of a continuous function is this. When they tell me that my function is continuous, they're telling me that my original function does not have any domain restrictions, that there's no domain restrictions that correspond to the original. It's nice, I can plot it. There's no points of concern, no domain restrictions for the original function. And I see the derivative function itself right in front of me. When I have to ask myself, does that have any domain restrictions? If it did, that means they would be new ones because the original function had none. So if this one had any, they'd be new and I'd have to write them here. When I look at this, I don't see any square roots. So no domain restrictions on what x can be. That is to say, if I had square root of something, I'm not allowed to have a negative value of x inside. So I would have to be cautious around a square root and say, x can't be negative in there. But I don't see such a thing or any expression involving a root. So I don't have any restrictions on a square root. I also don't see that this is a fraction. So there's no way for my denominator of this thing to be 0 because there's no denominator. So that is to say that my original function has no domain restrictions and neither does my derivative. So there are no new domain restrictions of the derivative. So I don't have any additional critical numbers. The critical numbers I got from this part are all that I have. If we move on to part B, where it says, okay, now that you've done all that, use the first derivative test to find the x value locations of any local extrema, we're going to do the same exact thing that we just did a minute ago and draw a number line. So when they say first derivative test, that means a number line analysis using the derivative. So let's put on our number line. We have it goes from minus infinity to infinity, and on this number line I'm going to have 3 x values, my 3 critical numbers. Put them in order. The -2 will come first, and then the 0, and then the 5. So I have 3 possible maxes or mins. And we're going to use the derivative to help me figure it out. So if I focus on the -2, I've got to see what my derivative's doing on either side of -2. Because I want to figure out if -2 corresponds to a local max or a local min. In order to do that, I pick a test point in those 2 regions and I plug those into the derivative. So pick a number between minus infinity and -2. It can be any number you want. Really, it can be anything. But let's say that I choose the test point -3. I wrote it in there real tiny, but -3 is what I'm going to choose. And let's say I pick a test point between -2 and 0. Now that's kind of a small gap there between -2 and 0. So let's say I picked -1. I have to plug test points into the derivative. Make sure it's the derivative function. Well, I suppose you don't have an option. All we have is the derivative function this time. So that's the only thing we can plug things into. But make sure it's in the derivative. I want to plug in f prime of -3. And f prime of -1, because I want to see what's going on either side of -2. When I plug in -3 into the derivative, all the way up there, we get 3 times -3, 5 minus -3 squared, -3 minus 2. Now, when you punch this out, you get -9 times 8 squared times -5. Now, unfortunately, let's see here, I have minus, I plugged things in a little wrong here. This is minus x minus 2. So when I plug in this, I have minus -3 minus 2. So I gotta be careful here. This is a double negative. Minus -3 becomes +3. 3 minus 2 is 1. So that's not -5 there, that's 1. Anyway, this is a really good argument for having a calculator. When you punch this out, this is a negative times a positive, which calculates out to be a negative. And that's ultimately what we care about here. We don't care much about what the exact number is, really. We just want to care about whether the derivative is negative or positive. If the derivative is negative, that tells you something about the original function. The original function has to be what? It has to be decreasing on that region. So for that test point I pulled -3 from, we would say that my function is decreasing. And then you go around and plug in the next test point, the -1. So let's do this one carefully here. We have 3 times -1, 5 minus -1 squared times minus -1 minus 2. So we get -3 times 6 squared, 1 minus 2. So we get a negative times a positive times a negative. You can punch this out if you like, but it would punch out a negative times a negative is a positive. It would give you a positive number. Because you get a positive number out from the derivative when you plug in -1, that means that your function is increasing there. Your original function has to be increasing. So from the region I picked -1 from, we'd say my function is increasing there. Now that I know what's going on either side of -2, I can make a conclusion about whether or not -2 corresponds to a local max or a local min. If I'm looking at it, we said my function's decreasing on the left of -2 and increasing on the right. So when you have a function that's going down on the left and up on the right, down and then up, down and then up, that means that it has to correspond to a local min. So I'm not done with all of this, but I know right now that x equal -2, that has to correspond to a min because I see a bottoming out right there. Now let's move on to my next critical number. My next critical number was x equals 0, and that one corresponds to a local maximum, a local minimum, or neither one. We have to figure out which one. At least I know that on this side of 0, my function's increasing. But let's figure out what's doing on this side of 0. So in this region, between 0 and 5, pick another test number. You might pick 1, or 4, or any other number. Take that test number and plug into the derivative. That's the derivative function up there. 3 times 1, 5 minus 1 squared, -1 minus 2. So you end up with 3 times 4 squared times -3. So I get, you can punch this out to verify, but when you punch this out, you will ultimately have some type of negative number. And because that value is negative, that means that my function, my original function, has to be decreasing. So I can come over here on this region that I pulled 1 from and say that my function now on that region is decreasing. Since I know what's going on to the left and right of 0, I can now make a conclusion about what happens at 0, if anything. If my function is increasing on one side of a function, increasing on the left and then decreasing on the right, increasing and then decreasing, increasing first and then decreasing, then it has to be that x value has to correspond to a local max. It's kind of neat that you can use the derivative to figure out what's going on with the original. My function's increasing, it's going up, and then it's going down. So if it's going up on the left and going down on the right, it has to correspond to a max there. Let's figure out what's going on with our last critical number, our last runner-up, 5. We don't know, maybe 5 corresponds to a local max, maybe it corresponds to a local min, maybe it's neither one. I already know what's happening on the left side of 5. We know my function's decreasing. Let's pick one last test point right here between 5 and infinity and see what my function's doing. So let's pick 6, say. It can be any number between 5 and infinity. Now we're going to pick 6 and plug 6 into the derivative. The derivative function's up there. You get 3 times 6 is 18 times -1 squared times -8. Now -1 squared is +1. So I end up with 18 times 1 times -8. And when you punch this out, this gives you some type of negative number. Negative times a positive. So this means that my function is decreasing on that interval I pulled 6 from. So my function should be decreasing right here. Now that we know what's going on the left side and the right side of 5, we can make a conclusion about what's going on there. Is it a max, a min, or neither? If my function's decreasing on the left side of 5 and it's still decreasing on the right, there was no turning point. There was no change. It just kept going right on down. Turning points, there has to be a switch from either decreasing to increasing or increasing to decreasing. There is no switch here. My function's still doing the same thing it was. Since there's no change from one to the other, there cannot be any local max or local min at 5. So here we would say none. There is no local max or min at 5. 5 is a critical number, but it doesn't correspond to a local max or a min. So if we write our conclusions down, I don't have a whole lot of space here, but we would say we found that there is a local min at x equal -2, and we say at the x value. We found a local max at x equals 0, and we didn't find anything happened at x equal 5, so we kind of leave that out of the conversation. We would say there's a local min at -2, local max at 0, and then that's it. Those are the x value locations of any local extrema. All right, that is it for this problem. Please join me for the next video so we can do the rest of these problems.